presentation, and yeah, I think this is going to be a bit interesting because, well, my supervisor is also the session chair, so if I don't graduate, I guess we'll know why. Okay, the title here of this presentation is Continuous Variable Quantum Computing on Encrypted Data. This is a somewhat weaker version of this homomorphic encryption that we heard about this morning. So, to motivate this, just talk about some of these cloud computing or cloud services that exist, where you would like your data to be secret, but you would still like the services that these providers they offer to you. So you would like to be able to sort and search and tag and so on. So there was this very nice result from 2009 that we already heard about for homomorphic encryption in the classical sense, where you will in principle be able to do Google searching on encrypted server terms, for example. So if we extend this to the quantum realm, we heard that fully homomorphic encryption in the quantum sense is a complicated issue and that not much is known about it. Certainly not in the continuous variable sense, maybe in the DB sense, I don't know too much about that. Then Broadbent and others in 2009, about the same time as the homomorphic encryption, the classical point of view came up with this idea of blind computing, which is the weaker version of the homomorphic encryption, in the sense that you still have your input and your output and your program, and you want some combination of these to be secret to the server that you're sending stuff to. But you're not restricted to just one round of communication per use. So for every state that you send to the server, you allow some amount of classical information on as well. And this allows you, in fact, to do better than you could for homomorphic encryption, but the protocol is in a sense weaker because you need more resources. Okay. And there's an even weaker version of this, which is quantum computing on encrypted data, where you give up this idea of having a secret program and you just say, okay, now I just want my input to be secret and I want my output to be secret, in the sense that the server doesn't know about it. But it knows, it's allowed to know what you want to do with it, so it knows the program. Right. And you're also allowed to use multiple rounds of communication. So that's what this work is about. But it's about this idea of quantum computing on encrypted data in the context of continuous variables. So continuous variable universal quantum computing. Okay. So maybe I should start by reminding you that universal quantum computing in continuous variables, you have these gates. You have the first two guys here are just displacements, basically. You have U2 gate, which is just a squeezing operation up to a phase shift. You have a QB. Basically, this is the guy. This guy is non-Gaussian and not really implemented, as far as I know. Then you have a Fourier gate and you have a controlled phase gate. Okay, so we have these 6 gates. One of them is non-Gaussian. Everything else here is Gaussian. It turns out that you need at least this guy. You need at least one non-Gaussian gate to implement the universal compute, because this allows you to generate operators in polynomials of the quadrature operators. And this turns out to be what you need. Okay. So the experiments that we did, that I will talk about later, basically are only concerned with these gates here. And then maybe we can discuss about these at another point. Okay. So moving on, the encryption operation that we want to implement here is that we imagine that we have some sort of input state that we want to send to this gate. And let's just say, for example, that this is just a vacuum state. Right? So the encryption that we want to do is that we move this guy phase space to some unknown location. So the server sees the state having a different mean value than the one that it actually has. Yeah. So on average, if we do this a lot, for a lot of different input states and a lot of different encryption values, you will end up with something that looks a bit like a thermal state. And ideally, you would like to have this displacement region, so you displace randomly around the phase space. You want this to be as big as possible because this allows you to confuse the server as much as possible. Okay. So that defines the encryption operation. So now we want to know how to decrypt again. So once again, the scheme is we have an input state, we decrypt it, send it to the server, it does one of these gates, or maybe a combination of gates, and then it sends it back, and we want to know that the decryption operation is actually feasible. Okay. So you'll notice here that for basically all of the gates, except the non-Gaussian one, the corrections are also just displacements, which is nice because we don't want the client to have too many quantum resources. So we don't want to require the client to have quantum resources. Except here for this one, where it turns out you do actually need the client to have squeezing. It turns out that, which is another nice property, that gate composition is also fairly easy in that you can just move your corrections out to the front. So you can have your server run an entire program and just correct for all of the combined gates of the program at the end. So you don't have to do it like a ping pong for every gate. Okay. Now U3 is special because it requires, and this is actually what comes back to the multi-round requirement here, that you need to put in two modes, and you need a measurement at the server, and the server needs to communicate the output of this measurement to you as the client. And this obviously needs to be classical information. Okay. So experientially, the scheme is something like this. For coherent states, at least. You have input, which is also just a displacement. You displace it for encryption. You transmit it through some lossy channel, because the server is presumably not right next to you. Then you perform some sort of gate here from this set that I showed you before, and you go back and you decrypt. And this decryption again depends on the program quality. Okay. So going back to the efficiency of decryption, as I said, you want as big as possible amount of modulation to confuse the server, to obfuscate what your input is. So say you have some family of input states, and you have a Gaussian distribution of modulations to obfuscate your inputs. Then the information classically between the input and or the client and the server is something like this. So obviously you want this guy to be huge. But then there are some technical limitations to why you can't keep increasing this indefinitely. Okay. So we did two experiments, one for the displacement gates and one for the squeezing gates. And here you just have, once again, fairly boring input coherent state. You encrypt it with some noise source. You transmit it through this lossy channel. The server again does a displacement, which is a combination of these two displacement gates. So X and B, E and Q. You send it back through this lossy channel, and you decrypt. In this case, it's easy because it's just the phase shifted noise that you put on in the first place that you have to cancel out again. Okay. So if you try to reconstruct the regular function that comes about from this, the one on the left is just the gate operation that, as it happens, without using all this encryption stuff. So this looks like it's placed state, as it should. But you see here maybe that on the margin distributions for the other one, which uses the encryption-decryption procedure, you see that it's been smeared out a bit. So we want to somehow quantify this, how our decryption operation somehow degrades the output. So one way to do this is using fidelity, defined using the density switches. And in terms of transmission, you see here that it's a bit all over the place. That's not really because of the transmission. This is in fact because of the stability of the setup. So this is some time dependence, how the setup behaves and how well you can cancel out this modulation noise which is used for the encryption. Another way to quantify this, but you see in general that it's actually about 97%, which is not too bad. Another way to quantify this is to use signal-to-noise ratio. So you have some signal-to-noise ratio depending on your input state. Then you should see from the server's point of view that once you apply the encryption operation, the signal-to-noise ratio drops, which is good. It increases a little bit because the server applies some more information. And then you decrypt again. And the difference between these two blocks here is exactly what happens when you decrypt perfectly. And the gap here turns out to also be crucially dependent on the size of the encryption operation. So if it goes too big, then you will have a bigger gap, which you're not interested in. So there's some sort of optimum. Okay, so that was displacements. The second one is the experiment regarding the squeezing. This is a bit more involved. You have, as before, your hidden state input, and you encrypt it, as before. You send it through your logic channel. This time, you send it through a PBS into a Faraday rotator, and into the squeezing gate. Now, this circuit down here is for detection of the reflection from the cavity. That houses your non-limit crystal that actually implements this squeezing operation, which is pumped from up here. So this is just the circuit that you use for locking cavity. So you have your input state here. You have online squeezing of your input state. Comes back out. It goes through the Faraday rotation in the other direction. Is then reflected, and the client receives it down here. And this time her decryption operation is also a little bit different, in the sense that she has a separate beam that is also modulated in the same way as the encryption was, but with a phase shift and some differences in gain depending on the squeezing operation that is known to you, because as the client you request what type of gate you want, and you know the properties of it. You interfere these two, and you lock them so that your cancellation or your decryption is optimal. And then you proceed to the detection case. So, here we have reconstructed the steps in this protocol. So you see once again the displacements. You see that once you have this encryption of a fairly large thermal state, you don't see the displacement on the scale. Then you apply the squeezing to this thermal state, displaced thermal state, and you recover the displaced squeeze state once you decrypt. So, once again, we would like to quantify this using fidelity. So there are two data series here. There's one where we have only the loss intrinsic to the setup and to the implementation of the squeezing gate. And we have one here where we also, in this channel here, we implement corresponds to 5 dBs channels. So once again, you see that there's some system drifts that make sure that these errors, they're not in fact statistical because of the number of data points, but they are stability issues and stuff. And you see that the lossy one is consistently above, which is somehow interesting because it seems to indicate that if you have a very lossy channel, then you can actually perform better in terms of decryption. Because you should keep in mind, this is not the fidelity of the gate itself. It's only the fidelity of the decryption operation. This says nothing about how good the gate is. This I will show you in a moment, because this is actually what shows up in the SNR picture. This just shows you how good the decryption operation is. And this performs better when you add loss, because essentially the loss makes sure that you are closer to vacuum, and if you decrypt poorly, well, you're still pretty close to vacuum. So it looks like you can do better. But of course, your quantum information is still lost. Okay, so if we look at the SNR instead, the input here is just, once again, the spaced state. And the decrypted output without the encryption we would expect to actually be up here if the gate was perfect. Because the excitation that we implement here with the coherent state experiences the same gain factor as the quantum noise does. So in fact, we wouldn't expect any change of it in the way that we define it now. So the difference from here to here is exactly given by how bad the gate is. And the difference from here to here essentially shows you the cost of the encryption decryption approach. Okay, so in conclusion, we have implemented a continuous variable protocol for delegated encryption universal quantum computing. We tested this on displacement and squeezing gates. We have investigated how loss affects this protocol, and we believe we have demonstrated the feasibility of this encryption scheme. The outlook for this is that we would still like a formalized security proof, because as I showed you, we can show obviously that with this decryption operation, the way we find it, that the mutual information between the client and the server goes down, which is good. This is nice, but we haven't yet shown that this is perfectly secure. So we haven't shown that there's some attack the server can launch to actually figure out the input. Another option in terms of outlook would be to implement with some of these harder gates. Maybe not the cubic phase gate, this is pretty far away probably, but implement with composition gates and show that you can actually compose an entire program and still just decrypt at the end efficiently. And lastly, to implement with more interesting input states than just simple displacements. Right. So that's it. Thank you.
Thank you. So any questions? Then I think we will go on to the last talk of this morning session, and this will be delivered by Christoph Marquardt.